Welcome to Mathmania Academy. In this in this video, we are going to solve the Part B questions of June 2015 CSIR net. We are going to solve only the questions that are asked from linear algebra. Okay, there were. Hope you all know in Part B there will be 12 questions in total from the Unit 1, that is from the analysis and linear algebra altogether. So in this year, there were 8 questions from linear algebra itself. So in this video, we are going to cover all the 8 questions. So the first questions here, as you can see, I have taken the question booklet C, and based on that, I am working out the. I have given the numbers to the questions. In the first question it is given that we are given a 4 by 4 real matrix A, and T is some linear transformation which is defined by TV is equal to AB, which means they are associating a matrix A. Okay, they are associating this matrix A with the linear transformation T, and the basis is not discussed here. So that is one of the basic result that we have studied. For every linear transformation, if it is defined from a finite dimensional vector space to another finite dimensional vector space, we can very well associate a matrix to it, and the order of a matrix is defined by the dimensions of the vector spaces that we are considering. Okay, here the domain and the codomain is R4, so the matrix is of order 4 by 4. Okay, and here the elements, the entries that we take from R4 are to be treated as a 4 by 1 matrices. Okay, 4 by 1 matrix means what? Something of, if I say I have taken this x from R4, then this x to be treated as x1, x2, x3 and x4. This is how we treat the entries of R4. Okay, now we are given 4 choices of the matrices, and we'll have to find the image of T and image of T to have the respective dimensions 2 and 1. Okay, what do we mean by the image? Okay, dimension of the image of a transformation. So that is just a minute. So dimension of image of transformation is nothing but the, is also known as rank of the transformation, which is nothing but the rank of the associated matrix. Okay. This is one of the basic fundamental result that is available in linear algebra. We can very well make use of this ideology to work out this problem. So if you have to find out the dimension of image of a particular transformation, you just find the rank of the associated transformation, which is quite easy, from which you can very well conclude the dimension of the images. Okay, so in order to find the dimension of T, it is enough to find, that is dimension of image of T, it is enough to find the rank of A, and here rank of A squared. Okay, these are the two things that we have to find. Okay, here if you notice, here, okay, it is very well given that the asterisk symbol denotes some non-zero entry. So rank of this matrix is 2. Similarly, rank of this matrix is also 2. Rank of this matrix is again 2, and rank of this matrix is not 2. Okay, so you can very well check these things, because there are two independent columns, non-zero independent columns. Here we have the same goes with the option 2 and 3, whereas if you come to the option 4, whatever may be the entries, these entries may get cancelled. Like only in these two positions we have the non-zero entries. The rank need not be equal to, actually the rank need not be equal to 2, it can be 2 or it can be 1. Okay, so we are not very sure of these things. Okay, now let us try to evaluate the A square. Okay, how are we going to evaluate? We will check if we have a non-zero entry at a particular position or not. Here, if you just see, in the third column and the fourth column, we have some non-zero entry, which means if in the third row, like when you multiply this row with this column, okay, this row with this column, you are going to get all the entries 0, right? So it is very clear that when you multiply up any row with first and second column, you are going to get 0 only, right? When you multiply your first row with the third column, only in the third and fourth positions we have non-zero entry, whereas in the third column we have 0 entries there. So it is done, right? And when you multiply this particular row with the fourth column, the first and second entries of the row are 0. So the first two entries will give you 0. The third entry has some non-zero entry, so that is going to give you a non-zero entry. The similar goes with the second column as well. When you multiply your third row with the last column, you are going to get 0. Anyway, here you can very well see that you have only one column which has non-zero entry. Therefore, the rank of a squared is 1. So, here in this problem, we were asked to find out the dimensions of image of t and t square. This is satisfying the requirements. So, this is the right option. In part B, there is only one right option. Okay, sometimes more than one option seem to be right. In that case, we'll have to choose the most appropriate one. Okay, for the matter of fact, let me give you the idea of calculating a square to the option 2 as well. Okay, you can just using the same ideology that I have told you, you can very well see you are getting non-zero entry here. Okay, just because 3 with 3, the same goes here too. Okay, and when you multiply this one with this one, you are again going to get entry here. The same goes here as well. So the rest of the entries would be 0. You can very well calculate these things. So this is also a right option. Okay, if you check the key answer of this particular year, you can note that option 1 and 2 are given to be right by the CSIR people itself. Similarly, you can calculate a square for the third and fourth option that does not have rank 1. Okay, it is not 1. Let us move to the next question. Here we were given three different mappings. Okay, and we are asked to check whether they are linear transformation or not. Basically, what is the property of a linear transformation? If you have a mapping which is defined from V to W, then if it satisfies T of alpha V plus V1 V2, let us take this way. Alpha of V1 plus V2, this has to be alpha times of T of V1 plus T of V2. If it's, and this has to be true for all the entries in V. Whenever we talk about the vector spaces, there is an underlying field in it. Okay, so here if we are considering two different vector spaces, these two are vector spaces over the same field F. So here the vectors v1 and v2 are taken from V, and the scalar alpha is taken from F. Okay, so what is actually happening here? If you just see, v1 and v2 are the entries from the vector space. Okay, alpha is a scalar from the field. When you make a product of the scalar with this vector, this is also a member of V. Since this is a member of V, this alpha v1 plus v2 is also a member of V by the property of a vector spaces, right? So you have taken an element from a vector space and you are applying the mapping. Since this is a mapping, the image will land in W. Okay, now we have treated everything as now we have calculated everything, and finally we arrived at a particular element in V. Now this the separate ones. Okay, this V2 is a member of V, therefore this T of V2 is a member of W. In a similar fashion, T of V1 is also a member of W, which means since W is also a vector space, alpha times of T of V1 is also a member of W. Now you are adding two vectors in the vector space W, and we will see that these two are equal. Okay, here if you notice, I am telling you the point here. The addition is addition that is defined in the vector space V, and this addition is a addition that is in the vector space W. Okay, we for this matter of simplicity we write simply plus, but we have to be very careful when doing the calculation. So this is the underlying concept. Now coming back to the question, you can very well check these things. This is by the definition. One small hint that I am giving you that will be handy when you do these kind of problems in examination. Okay, just see if you have any non-linear terms that are appearing in the mapping, that cannot be a linear transformation. Such things you can very well avoid. Okay, so whenever we talk about a non-linear thing, we do not encourage any constant to be present except 0. If the constant is appearing in a appearing alone, then we do not encourage it. If it is appearing along with some variable, okay, very well, we can encourage it to be there. Okay, in that case this cannot be a linear transformation because of this 4. Okay, that is when you apply f of alpha times of x1 y1 z1 plus x2 y2 z2, what will you get? So you can very well combine these things: alpha x1 plus x2, alpha y1 plus y2, alpha z1 plus z2, and this happens to be 4 uh, alpha x1 x2 plus alpha y1 y2. So this is what you are going to get. Now do this calculation separately. Alpha times of t of v1, that is this one. So this is going to give you 4 times of alpha x1 plus y1, right? Plus 4 times of alpha x2 plus y2. When you add these things, what are you going to get? You will get 4 alpha plus 4 upon alpha x1 plus y1 plus alpha x2 plus y2. These two will be equal only when alpha is equal to 4. Sorry, alpha is equal to 0. But that is not the case. This alpha can be any entry from the set of real numbers. Hence, it is not a linear transformation. In a similar way, you can very well check, because of this nonlinear term present in G, this is also not a linear transformation. Here you can check this is a linear transformation. Hence, only H is a linear transformation. Moving to the next question. Here we are given, let T be a 4 by 4 real matrix. Okay, such that T power 4 is 0. And Ki is defined to be dimension of kernel of Ti, which means I runs from 1 to 4. So we have 4 entries here. That is K1, which is dimension of kernel of T, and K2, which is dimension of kernel of T squared, and K3, which is dimension of kernel of T cube, and K4, which is dimension of kernel of T to the power 4. Right? So we'll have to identify which of the following is not a possibility for this sequence. So basically we'll have to find the values of K1, K2, K3, K4 and check which of the following is not possible. Right? This is what we'll have to do in this problem. Basically T to the power 4 is equal to 0, which implies what? So T to the power 4 is equal to 0. That implies T is nilpotent. Okay, but we are not sure this is the index of the nilpotency, because they have not given that 4 is the minimum value which satisfies this. Okay, there may be some value which is lesser than this also satisfies this. So that is what That is the main ideology that we have to keep in mind and proceed further. Okay, when this is the case, so when t to the power 4 is 0, we can very well see that the characteristic polynomial of this matrix is x to the power 4. Okay, by Cayley Hamilton theorem and the other stuff, other basic theorems, we can see that the minimal polynomial of a matrix divides the characteristic polynomial. So this gives us a hint that the minimal polynomial of this matrix can be either x or x squared or x cube or x to the power 4. Okay, so with which we are going to proceed further. And remember one more thing, here it is given that T is given to be a 4 by 4 real matrix, okay, satisfying certain conditions, but we do not know what actually the T is. So what do we do is that we whatever we'll have to speak for T, that can be spoken for the associated Jordan canonical form. That is what we are going to take. Okay. First of all, let us consider the case. First of all, let us consider the case when the minimal polynomial has the chance of being x. It means what? By Cayley Hamilton theorem, this also satisfies the this annihilates. Sorry, actually, the minimal polynomial annihilates the uh, given matrix. So, MT of t itself is t, right? This annihilates means this t itself is 0. When your t itself is 0, your t square is 0, t cube is 0, t to the power 4 is also 0, which means your matrix itself is a 0 matrix. So, in that case, what is the rank? Rank of t is 0, which means nullity of this t is 4. So this very well, the dimension of the kernel is what? That is the nullity of t. This is nullity of t square, and this is nullity of t cube, and this is nullity of t to the power 4. So basically we are finding the nullity. In order to find the nullity, we know that by rank nullity theorem, rank of t plus nullity of t is equal to the dimension of the domain, right? Here it is a 4 by 4 matrix, so dimension of r to the power 4, which is 4. Okay, so by writing it in a Jordan canonical form, that will give you the rank of t, and you know this nullity can be evaluated from 4 minus rank of t, right? So this is the ideology that we are going to employ in this problem. So your k1, k2, k3, k4 all are 4 in this case. Okay, now we are moving to the next case, that is when the minimal polynomial is x squared. When the minimal polynomial is x squared, when you write your matrix in a Jordan canonical form, you will have a 2 by 2 block for the eigenvalues. We know that for nilpotent matrices, the eigenvalues are only 0. Okay, this is one thing. The rest, this can also be a 2 by 2 block, or we may have two single blocks. This is also possible. In this case, what is the rank? The rank in this case is 2. In this case, the rank is 1. So when the rank is 2, okay, sorry, this is for t, right? Sorry, this is for t. When the rank is 2, which means your nullity is also 2. Here the nullity is 3, right? And proceeding further, if you calculate the square of this matrix, you just calculate the square of the Jordan canonical form. Whatever you speak for t is applicable for the associated Jordan canonical form. When you when you try to find out, if you treat this as your matrix t and try to find out what is t square, you get one non-zero entry in the second position, that is in the second position. So if you have any non-zero entry in the second column, then that will give you a non-zero entry. Based on that, if you look at this matrix, you do not have any non-zero entry in the second column, so this one will not give you any non-zero entry. In a similar way, the entry, this is in the fourth column, so if you just examine the fourth row, it does not have any non-zero entry, so directly your t2 is becoming, your t square is becoming 0. Here also the same case, your t square is 0. So which means in both the cases your nullity of t square is 4, since the rank is 0. So if your nullity of t square is 4, that is, then automatically nullity of t cube and the nullity of t to the power 4 are 0. Here what are the sequences that you are getting? 2, 4, 4, 4. This is the possibility, and the other one is 3, 4, 4 and 4. Okay, if you just see these options in that, 2444 is possible, 3444 is possible, so these two are possible. We are asked for not a possibility of a sequence, so these two cannot be the right answers, right? So now we move to the next case, that is when the minimal polynomial is x cube. Okay, in that case the associated Jordan canonical form would be, we must have at least one block of order 3 by 3. Okay, so 0 in the diagonal positions, that is the eigenvalue, and in the super diagonals we have 1, and the remaining is only one block. So in this case also the rank of this matrix is 2, and when you calculate t square, you can very well check there is one entry in the second row, so this will give you a non-zero entry. So rank of t square is not 0, it is 1. We do not have any entry in the third row, so this one does not contribute anything, but this one along with this one contributes something, so the rank is going to be 1. So which implies nullity of t is 2. In this case nullity of t square is 3, and when you proceed further, this is going to give us entry in this position, and we do not have anything in the third row, therefore t cube will be 0. Rank of t cube is 4, sorry, rank is 0, hence the nullity is 4. So this gives us the sequence 2, 3, 4 and 4. So this is also present in the option, hence it cannot be the right answer. Okay, so we are left with only this option. To this problem, this is the right answer. And if you have to check the last case also, that you can very well do. So mt of x is x to the power 4. In that case, in your Jordan canonical form, you must have a 4 by 4 block for the eigenvalue. Okay, so this one with this one will give you a non-zero entry. This one with this one will give you a non-zero entry. This will not give you any non-zero entry. Hence, the rank of t is 3. And when you go for rank of t square, that is 2. And rank of t cube will be 1. And finally, the rank of t to the power is, t to the power 4 is 0. Hence, nullity of t is 1. Nullity of t square is 2. Nullity of t cube is 3, and then the nullity of t to the power 4 is 4. Therefore 1 less than equal to 2 less than equal to 3 less than equal to 4 is also one of the possibility which is not listed in the options. But for this data, what are the possible options that I have showed you?